Hello guys, my name is Aaron Romero and I will be talking about fatty acid synthesis. Before I begin to talk about the process, I would like to emphasize that fatty acids play really important roles in the cells. For example, they can act as fuel molecules and they can be stored as triglycerols or triglycerides. They are also the building blocks of phospholipids and glycolipids, which form the main structure of the plasma membrane. Fatty acids derivatives can also serve as hormones and act as intracellular messengers. So I would like to emphasize that fatty acid synthase occurs in the cytoplasm. The process begins with malonyl-CoA as the substrate. So before the process begins, acetyl-CoA must be converted to malonyl-CoA. This reaction is going to be catalyzed by acetyl-CoA carboxylase, which is an enzyme that has a cofactor, biotin. So essentially, we are adding this carboxyl group into the acetyl-CoA. Biotin needs to be carboxylated, and this reaction occurs under the presence of ATP. So ATP hydrolysis occurs, and biotin is attached to the carboxyl group. So then this carboxyl group is going to be transferred to this. It's going to be transferred to this carbon, and this is going to give us the malonyl-CoA. The next step is the transfer of malonyl-CoA into ACP protein, which is an acetyl-CoA protein. So this is going to be transferred into this. So this is going to be our final product. So the next step involves a new acetyl-CoA. So the new acetyl-CoA is going to attach to a cysteine residue, which I believe is part of the ACP protein. This is going to be our the next reaction. It's going to be a condensation reaction, or essentially the carboxylation reaction. So malonyl ACP is going to be decarboxylated by beta ketoacyl synthase. So essentially, this carboxyl group is going to be removed. This is going to allow for this carbon to attack this carbonyl group right here, and this is going to displace the cysteine and sulfur residue. And our final product is going to be acetoacyl ACP. The next step is a reduction reaction. So acetyl ACP is going to be converted into hydroxyl butyryl ACP, and this reaction is going to be catalyzed in the presence of ketoacyl ACP reductase, and this is going to require an NADPH, and NADP plus can be the byproduct. So essentially, we added this hydroxyl group into the third carbon. The next step in the reaction is going to be a dehydration reaction. So we're essentially going to remove water from this molecule. So this reaction is going to take place under hydroxyl acyl ACP dehydrase. So we're essentially going to make an alkene right here. So we're creating a double bond between the second carbon and the third carbon, and so this is going to give us the butynyl ACP. The next step is a reduction reaction, which is catalyzed by eno ACP reductase, and this is going to give us butyl ACP, which is essentially the final product of the first cycle. So this reaction is also going to consume one NADPH, and our byproduct is going to be the NAP plus. So this is going to be our final product, butyl ACP. So this is, as I already mentioned, this is going to be the end of the first cycle. And I just want to emphasize that one ATP was consumed in the conversion of acetyl-CoA into malonyl-CoA, and we also consumed 2 NADPH in a reduction from acetyl acyl ACP into hydroxybutyryl ACP, and another NADPH was consumed in a reduction from butanol ACP into butyl ACP. So essentially, after this step, the whole reaction is gonna be repeated. So this growing HCl chain is going to be transferred into a new acetocysteine residue, and this whole process is going to repeat again. So the transfer from butyl ACP into the acetocysteine residue is going to displace the acetyl carrier protein, and so this protein is going to bind to a new malonyl CoA, so that the reaction can happen again until we reach this product, palmitoyl ACP, which is essentially converted into palmitate. So this is our final reaction in the process. So palmitoyl ACP is going to be converted into palmitate. This reaction is going to be catalyzed under the presence of palmitoyl thioesterase, and this is going to be dehydration reaction. So water is going to be used, and this is going to be our product. This is going to be the byproduct, and we form palmitate, which is essentially a fatty acid, which it's a fatty acid, most common fatty acids in mammals. So I just want to emphasize the overall net reaction. So we used a total of 7 malonyl coenzymes and a total of 7 ATP in the conversion from acetyl CoA into malonyl CoA. We also used 14 NADPH in the reduction reaction from acetyl ACP into hydroxybutyl ACP and butanol ACP to butyl ACP. I would also like to emphasize that we began with the 1, 2, 3 carbon chain, and at the end of the first cycle, this chain, malonyl ACP was reduced into 4 carbon chains, 1, 2, 3, 4. So we essentially this is essentially mostly reduction reaction. So this is it for this is how a fatty acid synthesis process works.